All right, lesson 2, let's get mathy. So now what we're going to do is move on to doing some calculations about equilibrium. So remember, there are conditions for a system to be at equilibrium. Condition number 1 is at the microscopic level, the rate of the forward reaction must equal the rate of the reverse reaction, and they will be constant. Because of that, at the macroscopic level, the concentration of the reactants and products will also remain constant, but they are not equal. So with this idea of there being constant concentrations, we're going to introduce something called an equilibrium constant. It's given with the letter K for constant, because you know everything makes sense. And then we have this subscript, which is our identifier. So this is K, which is our constant of equilibrium. So again, like I was stating before, because the concentrations don't change, we can say that the ratio of the reactants to products will remain constant, and this is all at a given temperature. So the equilibrium constant is calculated by doing the ratio of the products to the reactants. So the concentration of the products divided by the concentration of reactants. Now, just a little side note, the concentration of reactants and products may change due to a shift in equilibrium. So we're going to be talking about maybe Le Chatelier's stuff and talking about what happens when there's a shift. But when there's a shift, the ratio of products to reactants will always remain constant. So you can kind of picture those graphs that we were working on, and you know, everything comes back up and comes back down until we're at this constant spot again. So how do we write equilibrium constants? Well, if you have a reaction like Fe3 plus SCN minus forms FSCN2 plus, this is our product, and these are our reactants. So we would do the concentration of the product divided by the product of the concentration of the reactants. That came out really weird because I had to say product twice. But really, it's products over reactants. Let's look at another one. So if I have two HIs forming H2 plus I2, I just pause because I feel like I should say the actual names, but sometimes that gets bogged down. So we've got our reactants and we've got our products. If we look at this, we have two HIs on the left, which could be written as HI plus HI. So two hydronic acids are going to collide, and when that collision occurs with sufficient energy and correct alignment, they form hydrogen and oxygen. When we look at this as a ratio of products to reactants, you've got your products, hydrogen and iodine, divided by, and we had two reactants here, HI times HI, and so we would simplify that as HI squared. So, in general, if you have reactants to products, you always do products over reactants, and each of those is a product within them, right? Multiplication. And then if there's coefficients, they become the exponent on the concentrations. So in an equilibrium expression, the stoichiometric coefficients have become the exponents, and there is no units for KEQ. So we're not talking about grams or moles per liter or anything, and this is because it's always a ratio. So the units would cancel out. So let's practice. So we're just going to take these two examples and write their expressions for KEQ. So KEQ equals products over reactants. So for this one, I have a nitrogen product, and it's going to be multiplied by a hydrogen product. Because the hydrogen has a coefficient of 3, that's going to become the exponent. And then my reactant is just this ammonia, so I'm going to have NH3, and then the coefficient becomes the exponent. All right, pause the video and give the next one a go. So for this one, I hope you notice that I just flipped the reaction around. So this time the ammonia is going to go on the top. So it's going to be the ammonia squared divided by the nitrogen times that hydrogen cubed. So we haven't put numbers into here yet, but I just want to kind of plant the seed in your head that reactions are reversible. So if we wrote it as ammonia getting broken down into nitrogen and hydrogen, this is our equilibrium. Whereas if we wrote it in reverse, where we have this reaction of nitrogen and hydrogen making ammonia, our KEQ would be what? Like, how would you describe the difference between these two KEQ expressions? if you're mathy, maybe you would use a word like reciprocals of each other. So if I told you that the KEQ value for part A was 5, then the KEQ for part B would be a fifth, right? So ratio of products to reactants would just flip. And now there's just a little bit more to this puzzle, which is equilibrium constant expressions, including solids or liquids. Let's just think about this for a second. So if we had a reaction like calcium carbonate forming calcium oxide and carbon dioxide, you, from what I just taught you, would be inclined to put calcium oxide times carbon dioxide divided by calcium carbonate, right? But let's think about things from a concentration perspective. When you have a solid, so there's a diagram of a solid over here on the right. If I look at the concentration at any point in this solid, it actually can't change. So even if part of this solid reacted, so let's say some of it reacted with the outside molecules coming in and reacting with it, the concentration inside would not be affected. It's not like gases where you've got these molecules binging around inside, and so when there's a reaction, something happens and it changes the concentration inside. With a solid, concentrations are actually constant no matter what. So if we think about that, the two parts of this reaction that were solids actually can't change in concentration. So this calcium oxide and the calcium carbonate are actually constant concentrations. If you think about the definition of this being a constant of equilibrium, those two things actually belong on the constant side of the equation. They'd be part of the things that don't change. So if you notice this, now on the left-hand side, we have an expression that's all constants. And on the right-hand side, the only thing that's driving this change in concentration would be the concentration of the carbon dioxide. So we don't include the solids, and we would just say KEQ is equal to carbon dioxide. So when you think about things that could change, you only want those things left because everything else remains part of your constant. So the key idea here is that you're only going to include concentrations that can change. This includes things like gases and aqueous solutions, right? Because ions can precipitate out or, be bubbled out as gases or whatever. But the key thing is that you have to exclude things like solids and pure liquids because the concentrations with there don't change. Now, just a little note on liquids. Liquids can be kind of tricky. For a liquid not to count, it has to be a pure liquid by itself so that the concentration is constant, which means that it's the only liquid on both sides, I'll fix that typo, on both sides of the reaction. As soon as it's mixed with another liquid, the concentration can change. So let's just make this clear by doing a couple examples. So I've got 3 examples here, and we just have to decide what is going to be included in our KEQ expression. So let's go through first off and just cross out all of our solids because we know that solids are never going to be included. Then let's take a look at our liquids. Now, liquids are only included if they exist on both sides of the equation or they are, well, that's the easiest way of saying it. So if we look on this example first, we've got a solid and a gas forming a solid, a liquid, and a gas. This water is the only liquid on both sides of the equation, so see ya. Same thing in this equation. We had a solid on the right-hand side. On the left, we have a gas and a liquid. So this liquid is a pure liquid, and we would not include it. On this last example, we have a liquid on the left and a gas, and then we have a liquid on the right and a gas. Should we include these liquids? Yes, because they are not pure because they're not existing on only one side of the equation, which means there'd be a mix of these two, and then as the reaction is progressing, you're going to have a change in their concentration. So what's left? So for this example up here, my only product left is the concentration of carbon dioxide, and then on my left-hand side, it's the hydrofluoric acid, and because its coefficient is a 2, I would square it. For this next one, when we look at it, when we look on the product side, there's nothing. So we actually just put a 1. It's a placeholder. And then in my reactants, I have a chlorine gas. I don't include states in my equilibrium constant expressions. When I was looking at Hebden, they sometimes do. I just find it too much. I think maybe if I was trying to really remember not to put solids in, it might be a good idea to put states, because then you'd be like, oh, I just wrote solid. But I am lazy and I just tend to leave them out. And then this one, we didn't get rid of anything. And so for this one, it would be the concentration of CH3COCH2Cl. Don't even want to attempt to say that one, times hydrochloric acid, divided by the CH3COCH3 times the chlorine gas. And none of them had coefficients, so there's no exponents. Awesome. All right, go give that stuff a go.